So today, I'm going to explain the confined quantum system. So we know that the title of my talk is Exploring Confined Quantum System, Virial Theorem, Degeneracy, Optical Response, and Information Theoretic Insight. So in the last 2 3 years, last 4 to 5 years, I have done, I am going to discuss with you. It's a already a known fact that confined quantum systems actually alters the electronic structure, physical properties of atom molecules and materials. They change their physical as well as chemical properties. Moreover, they change their coordination number. Actually, what happened when we put confined system under confinement, particularly in high pressure regime? Usually in free condition, the atoms or in a system are away from each other and they have certain van der Waals space allotted with them. But if we increase the pressure initially, then the van der Waals space get reduced. If we see this first and a second picture, it's even very clear that when a free condition, the void space is very high. However, when the pressure increases, the void space become narrow and they come very close to each other, and that lead, moreover, in such situation, the highly charged anion, which are usually diffused due to high electronic localization, gets compressed here, and that leads to the changes in properties of the system. Particularly if we see that the interatomic and intermolecular distances become very close, and that leads to increase in covalency on the systems. Moreover, in thermodynamic point of view, if we check, then we found that the free energy, which contain the energy on PV term and one TS term, the contribution of the PV term dominates because the entropy of the system becomes very slow as we have compressed in a very narrow range. However, the pressure is very high, it may be 100 gigapascal. So that leads to blow up of this pressure, this PV term, and the energy also gradually increases. Further, if we move again, when the pressure increases, it's not in general, the bond length decreases. Sometimes bonds gets elongated, sometimes bond get compressed, leading, and finally, if they become very close to each other and crowding occur, and this crowding first alters the orbitals of the system, and once this rearrangement of orbitals occur, that leads to the changes in their coordination number, and that particularly that change is positive, means it increases, and that increase in coordination number leads to the formation of several new metallic polycenter or multicenter complexes under high pressure, which is not possible under free condition. Now, if we see the structure and rearrangement of the orbital, then we can see that due to this rearrangement of atomic orbital, their periodic train changes. And orbital rearrangement gives them generation of new states. So if we classify this new confinement, it can be classified into 4 different parts. Impenetrable sharp. The example is the high pressure confinement, where we are trapping the atoms or molecule under extreme pressure. Next, impenetrable smooth. That means we are trapping it in impenetrable condition, but it is not that strong. Just one example is that trapping of atoms and molecules under harmonium environment. Next comes the penetrable sharp. The pressure, the potential is very strong in the region, but it's not that intense like high pressure region. Next is the penetrable and smooth. Penetrable and smooth, where the ideal example is trapping of molecules under supramolecular cavity like fullerene, or nowadays it's very like molecular MOF environment like molecular metal organic framework. This impenetrable sharp, penetrable smooth, and is actually explains the nature of the potential of the system. Impenetrable shaft means the potential is infinite, just like we are trapping a system in a particle box, and that's is infinitely barrier. When we moves to impenetrable smooth, then barrier is infinite, but it's not barrier is gradually increasing, as I give the example of harmonic environment. When we move to penetrable shaft, then both the boundary is tunneling may occur, but the potential is not continuous. It's fixed at the after a certain particular point. However, when we move to penetrable and smooth cases, then both changes simultaneously. Means potential is a continuous form, and it is changing with increasing length. Solving such confined quantum system is very challenging, because particularly in high pressure condition, when the system is trapped under extreme pressure, then conventional basis set fails there, as the conventional basis sets has an asymptotic tail and they got vanished at r tends to 0. However, in confinement cases, the particle is available, or atom or a molecule available within a range. So in that case, the conventional basis set is not applicable. So we have to find some new basis set, but at this moment, no such basis set is available in literature. In certain cases, people use plane wave basis and pseudo potential approaches to study confined quantum system, but that are also periodic system, but not for a single molecule or an atom. In this case, in this context, we have used some numerical strategy, because these numerical strategies are alternative for this confined quantum system to solve. We have used generalized pseudospectral method to solve one electron system, and numerical Hartree-Fock strategy for more than one electron systems. And for solid calculation, for the crystal, for material calculation, we have used quantum expression. We have here mentioned also the Euler's variation context, but Euler's variation is a very good option for confined quantum system. But the challenge is that with increase in number of electrons, the variation space increases, and also the number of coordinate increases. So that makes it even more difficult computationally. So let us start with the exact model of confined quantum system. We have took one cell confinement model. If we see the black dot, then the atom, then this is the center of the system, and there is one blue circle, another is violet circle. You can that we call these from the radius RA when we have from origin to blue circle, whereas the radius RB, which is called the outer radius, is from origin to the violet boundary. So this is called a generalized confinement model. When our inner radius is 0 and outer radius is infinite, then it's a normal free hydrogen atom or free system. If we keep RA at 0 and make RB finite, then we have a confined system. Now, if we shift RA and make both RA and RB non-zero finite number, and RB is greater than RA, then it's become a shell confined system where the atom is trapped in a shell. And last option is RA, we make RA is finite and RB is infinite. In this case, instead of assuming the point charge model of the nucleus, we are assuming that nuclear has a finite size. So it has a inner radius is finite, and that's why we get left confined hydrogen-like system. Now, for such system, if we study the degeneration, if we study the energy spectrum using the pseudospectral method, we will find an interesting phenomena that if by controlling the nodal position of the system, we can generate a huge number of degenerate states, and that those degenerate states have the same energy with the free system. Suppose we take an example of n equal to 2 for the free hydrogen atom. So the energy will be minus 1 z, and z we took z1 equal to 1. So energy will be minus 1 by 8. And if we take that n equal to 2, then we will have total n equal to 2 into n plus 1 means 2 into 3 6 plus n plus 2 means 4 degenerate states. And with increase in n, such degeneracy will increase. If we see this table, then it will be very easier for us to explain that with increase in n, the number of isoelectronic pair is increasing. And let us take pictorially. We have chosen here the 4s state. The 4s states has 3 nodes, and the 3 node present here. This is the wave function for the 4s state of the free hydrogen atom, and this point is the first node. This is second and third node. If we place this node, and this free system has energy of 1 by, in the previous slide we have seen 1 by 30 minus 1 by 32. Now this similarly, if we place the boundary at RA, we will get one state with no node, and that have the same energy with the 4s state. Again, if we take the boundary from RA to RB and we take this wave function, then it is a one node system and energy is same with the free hydrogen atom. So by controlling this boundary, we can generate 10 such states, and all these 10 states associated with the 4s orbital, and they have the same energy. This degeneracy is due to the confinement, and this by changing the not changing but by controlling the RA and RB, we can calculate the position, and we can control the position of the node and find desired target energy states. Now as we discuss that in confined quantum system, the basis set is not applicable. So conventional theorem that are applicable for free system are no longer valid. In many cases, they fail to explain what happened in confined condition. One such example is virial theorem. The conventional virial theorem failed to explain the necessary condition for confined quantum system. So we need a new virial-like expression for confined quantum system. So based on that, we design a new virial-like theorem for confined quantum system, and this is the primary expression, and the expression is very interesting. We can see that the standard deviation square of kinetic energy and standard deviation square of potential energy are same. Even we can modify, we can comment in that way that total energy of the system is sum of the kinetic energy and potential energy of the system. And this equation suggests that the error associated with the ground kinetic energy is exactly equal to the error associated with the potential energy. And more importantly, the two average value, one is the kinetic energy average, another is the potential energy average. If we combine them, then they are giving the exact energy. So that means the error associated with kinetic energy may be cancelled by the potential or vice versa. So based on that, we design two conditions for confined quantum system. One is necessary condition, which is just analogous to the first expression, and second is the sufficient condition. Why I call it a sufficient condition? Because in variational context, we instead of using energy minimization, if we use this expression, we can calculate variationally optimized wave function. So, and moreover, that the expression designed here are applicable for both free and confined condition. So finally, we have designed a virial-like expression which is applicable for both free as well as confined condition, and this is based on the theory where the error associated with the kinetic energy is exactly equal to the error associated with the potential energy of the system. Now, if we take an example of this system for two examples where impenetrable and penetrable condition, we find that they are very good agreement with the hard and soft confinement conditions. Now we move to study the trapping of plasmas under high pressure. What does it explains? We know that with increase in temperature, the plasma tail effect predominates. So if this can be modeled by trapping a plasma inside a sphere, and if we gradually increase this with sphere of radius RC, if we gradually increase the radius RC, then this is just nothing but increasing temperature, and more we increasing temperature, that means more we increase RC, the tail effect will predominate. So based on that, we have modeled these three plasmas under confined condition and studied their properties. Before that, we have explored that the state deletion or collapse of bound state in plasma system can be explained by Shannon entropy. How? Because we know that in a plasma system, with increase in screening constant, the number of bound state decreases, and at one point all the bound state collapses. So we took the ground state results and try to analyze and find that when the bound state collapses, the energy of the plasma becomes positive. So a sign change occurred there. So now our objective was to check, is there any other option or any other possibility by which we can study the collapse of such bound state in plasma system? And we found that Shannon entropy at that point of collapse jumps infinitely. If we see these plots, then we can clearly see that there is a significant jump of entropy. We have here done our results for different Z values, means different charges, and found that with increasing charge, such collapsing point gets right shifted. So in all the cases, at the collapsing point, Shannon entropy jumps abruptly, and the position of such jump or position of that point gets right shifted with increasing charge. Now we also study the metallization in hydrogen atom, because in highly condensed metal in spaces, particularly in jovial planets, hydrogen atom found in metallic conditions. And in recent years, it has been found that at 400 gigapascal, hydrogen atom can become a metal. So based on that, we were trying that, is it possible to find such metallization condition for confined hydrogen atom? And another point also drives us that hydrogen is the most abundant element in the universe. So to see this, what we did, we stick on the formula derived by Hylarus in 1927. And Hartsfeld gives this criteria that if the dipole polarizability versus volume ratio is greater than 1 for a monatomic vapor, nearly cubic solids, or monatomic liquid, then they become metallic. But in free condition, it's not possible to use this criteria to find the metallization of a system, because of volume for a free system. To calculate the volume of a free system is a big challenge. But we took this idea and applied this for a confined quantum system and find that this Hartsfield assumption can be useful to find the metallization. And we see that not in ground state, but particularly in two states, hydrogen atom become metallic at certain values. But the problem is that there is no ground state metallization present. We cannot predict the ground state metallization using this criteria. So in that context, what we did, we incorporate a scaling concept to incorporate the effect of charge, screening constant, boundary effect, and boundary effect in the criteria. And because all these factors influence the electron density and also the polarizability of the system as well as the volume. So to do that, we have modified the existing Hartsfield traditional criteria into different form, considering some charge, screening constant, radius, and inner and outer radius criteria. And based on that, we found that in many cases, that is HIT term is hidden metallic states. Hidden metallic states are found in different states at certain characteristics points. Just like for confined hydrogen atom, when Ra is 0 and Rb is non-zero, then we can see that the metallization can be seen at 2p and 3d state, but not in S wave states. However, previously we have seen that in shell confinement condition, metallization can be seen in shell confined condition. Now, when we modify the cases, there are several HIT arises. In one state, we have seen it, but for two state, there is no such cases. But even in higher states like 2p and 3d, old Hartsfield was unable to explain the metallization in shell confined condition. But here we found that hidden metallic states are available. But the problem is that, so based on these 2-3 parameters and incorporating them in the expression, we have designed new metallization condition of hydrogen atom under extreme pressure, and to some extent it can explain. It cannot explain the whole phenomena, but to some extent it can. And there are options to develop new criteria, particularly if we replace the polarizability of the system by dynamic polarizability. We were using the static polarizability for this calculation, but if we change to dynamic polarizability, then the situation change. So in future, we will try to explore that. Now we move to design quantum material using quantum expression. Why we design such materials? Because unlike the other systems, usually carbon allotropes, one of the most abundant material and the fundamentals of the organic chemistry, the carbon, which usually in room temperature is conducting and atmospheric pressure. But if we increase the atmospheric pressure to gigapascal range, their insulating properties decreases. So keeping in mind that point, we were trying to design some complex or some material for based on carbon atom or carbon allotropes, where its conducting properties increases with increase in pressure. And in that context, we have designed a sp2 sp3 mixed hybridized carbon architecture, where the system become conducting through a sp2 channel, and they are stable up to, if we check their enthalpy versus pressure curve, curve, they are stable up to 47.2 gigapascal, and they are, and their hardness is very high. So this checking of hardness ensures that if we apply more pressure, they are not brittle and they will not break down. So that ensure that we can apply them, put them under high pressure, and if we put them under high pressure, so they are stable up to 47.2 gigapascal, and at that region they become conducting. And this conductivity is through a 1D channel, and the high, the most, it become highly conducting, and the peak will be observed around 11 to 26 gigapascal region. So these are the observations so far I have got while starting the confined quantum system, but we have to do a lot of work, and I have just started. And our primary challenge is to design an optimum method for confined quantum system, and in fact basis set free method, and we are working on it. And then we use the relative information based measure for such confined quantum systems, and particularly in many electron domain. So far what I have done, a little calculation in carbon allotrope and some in hydrogenic form, but not in many electron atoms and molecules. But that challenges is due to that method. So our primary focus is to design some appropriate method for that. And once it will be available, maybe the quantum computing based architecture and VQE based algorithm will help us and to solve these cases. So maybe in future we can update you about the appropriate method for the system. So before ending, I thank Professor Panigrahi for giving me this opportunity to present my work. Also QSQT for the same, ANRA PMCRG for funding, and UGC DAE CSR for research funding. Thank you.
Thank you very much, Dr. Neetik Mukherjee. Now the floor is open to a couple of quick questions.
Is this confinement will be applicable by? Am I audible?
Yes, sir.
Yes, you are audible.
Yeah, I believe that you made confinement by increasing pressure, but normally
Yes.
Confinement is by reducing dimensionality of the material, quantum wide,
Yes.
quantum dot.
Yes,
will it work the same pattern?
No, sir. This is just, in this case, what I am doing, I am just reducing the available space. So in that one to space, 2, nothing. This is just changing the boundary condition. So that confinement is
may be same, but eigenstate as you are getting many, they may not be also. Na? This will
Yes, sir.
Okay. Thank you.
Neetik, I have one question. Yeah, sure.
Yes, sir.
Yeah, please, Professor Panigrahi, I will ask after your question.
Mine is very simple. So, Neetik, in many natural systems, a metal ion inside with a sort of carbon or porphyrin ring outside is preferred in nature, right? So in that way, so how, I remember we were talking about this fullerene with some metal inside. Have people sort of thought about it or realized it as a quantum qubit?
Sir, it can be, but I have not seen. I will check and then I will update you, sir.
You can talk to Anantarashmi madam also, because she knows about it a bit more later. Yeah.
Yes, sir.
Okay, Ranjit Singh.
Yeah, I have one question. So thank you for a very interesting and informative talk. It's a continuation of Professor Panigrahi's question, it seems to me. In quantum technology, we use heavily non-separable states, entangled states.
Yes,
so how easy it's to prepare and manipulate these such states in system which you have considered?
Sir, these systems are in general, if we think it in an experimental point of view, that how the high pressure states can be generated. Actually, you take in the tip of the diamond unveil cell and then apply high intensity laser and high frequency laser to design them. So if we can control that, then we can control this system. And in fact, I am trying to do that in theoretical context, that by controlling the laser, can we modify this their properties with our desired target. So I can give you some example that in case of that magic frequency, there are there are two concepts of tune out frequency and magic frequency. They are associated with the polarizabilities of the system. So in this in this quantum material, where the states for the qubits, we need the such a system where the polarizability is not so very high and also not very low. There should be optimum. So by controlling that magic frequency and tune out zone, we can design those target state with target polarizability. That may help. This is my guess. That may help. One thing. And second, when the magic frequency comes, it gives us information about a multiple state with same polarizability. So if it at a particular wavelength, so if that comes, then it may help. But in future, I can update you about that.
Thank you.